Hi everyone. So what we're going to do here is we will start our study of organic chemistry by basically defining what organic chemistry is. So if you look through any textbook, any resource, what you would find is organic chemistry is defined as the study of carbon-containing compounds. So it is carbon-containing compounds. That means carbon is one of the elements that constitutes these compounds. Because going back to Gen Chem, remember that compounds contain more than one element. So there are other elements that are present in these compounds or elements that combine to make these compounds. Carbon is sort of like the backbone, but other than that, what we have are usually hydrogens. You would see a lot of hydrogens in organic compounds, majority of organic compounds, okay? There are some organic compounds which may not have hydrogens in them, okay? But other than that, other than carbon and hydrogen, organic compounds also contain nitrogen and oxygen, and then halogens in them. Sulfur, phosphorus, these things are also possible. So that's why we just define it based on what's the backbone or the skeleton, you know, so it's a carbon containing compound. So what we'll do here is we're going to use carbon as our model, and then we will review some of the concepts from general chemistry so that we are ready to move on to some of the concepts in organic chemistry. So as you might all recollect, carbon has an atomic number of 6. Okay, in fact, I'm going to write this here. So carbon's atomic number is 6, and it has a mass number of 12. And again, just as a quick review, the atomic number, okay, so this is the atomic number, and this is atomic mass, or the mass number. The atomic number, this equals number of protons or number of electrons in the nucleus. That's what this number represents. So when carbon's atomic number is 6, it means that carbon has 6 protons and it has 6 electrons in its nucleus. The atomic mass, on the other hand, this represents the number of protons, and so notice how this is an and, so that's a plus, okay? Number of protons and number of neutrons in the nucleus. Okay, so it's the number of protons and the number of neutrons. So carbon's atomic mass is 12. This number represents the number of protons and the number of neutrons. We already know the number of protons based on the atomic number. So that means carbon has 6 protons. So that actually helps us calculate the number of neutrons, which should also be 6. Because that's how much is left out of 12, okay? So atomic number and atomic mass. Two concepts from general chemistry. We don't really need this, but I think it is useful to basically get started over there. Now, the next thing we're going to talk about, again using carbon, is electronic configuration. So electronic configuration, this basically tells us how electrons are filled into the orbitals outside the nucleus. Because going back to a very crude structure of atom, okay? A very crude structure of atom, realize that an atom has what we can call the nucleus, okay? The atom has a nucleus. the nucleus contains protons plus neutrons. And outside the nucleus, we have various orbitals, and this is where the electrons are present. Again, I'm just considering a very crude model of an atom, okay, what an atom is. So outside the nucleus, we have orbitals, various orbitals, and the electrons are present in these orbitals. Now, the orbitals, recollect from Gen Chem that these are 1s, 2s, 2p, 3s, 3p, and so on. Okay. For organic compounds, we rarely have to go beyond a 3p. Okay. And in fact, we would mostly be limiting ourselves to the 2s2p because we're going to talk about the second row elements: carbon, nitrogen, oxygen, and the halogens. So those are the ones that we'll be mostly talking about. So if that's true, then for carbon, we actually don't need the 3s and the 3p, or in fact, for nitrogen or oxygen, we don't need 3s and 3p. So for carbon, since its atomic number is 6, which is basically the number of electrons, we can start filling in the orbitals. So it should be 1s2, 2s2, and 2p2. That is 6 electrons. Now, again, we also learn in Gen Chem to fill these electrons into boxes. So remember how we can represent the 1s by a box, the 2s by a box, and then the 2p. How many 2p orbitals are there, or p orbitals are there? I hope you remember there is px, py, and pz. So the 2p, there are 3 orbitals. Okay, so we have a px, we have a py, and we have a pz. All of these are 2p orbitals, and they are degenerate. That means they all have the same energy. All of these p orbitals, they have the same energy. So the 2p orbital has 2 electrons. Again, going back to Gen Chem, the Hund's rule of maximum multiplicity. Recollect that electrons are first filled into the orbitals singly before you start pairing them to maintain the maximum multiplicity possible. So for the 2p2, we're going to fill the first electron, so 1s has 2 electrons paired, 2s has 2 electrons. Now, we cannot singly occupy 1s, 2s, 2p, x, 2py, 2pz, and then come back and fill the 1s and the 2s again, because these are of increasing energy. Okay, so the 1s orbital has the lowest energy, so you have to fill it completely. And then the 2s is the next one, you have to fill it completely. When you come to the 2p, you have 3 orbitals, which are all equal in energy. So this is where we're going to first singly occupy the orbitals before we start pairing electrons. So for 2p, we have 2 electrons in the p orbital. So we put 1 electron in the px. Now I could put it any of these orbitals. It could be in py or pz. Okay, so we can put px and then py, and basically we've exhausted all of our electrons. So this will be the electronic configuration of carbon in its ground state. Okay, we're going to call it a ground state electronic configuration, because we will see an excited state electronic configuration later. Okay, so that's the electronic configuration. And from the electronic configuration, we can also talk about what's called the valence electrons. This is the number of electrons in the outermost shell orbital. Okay. So for carbon, the outermost orbital is the second orbital, or the 2, not the 1s, that's the inside. So these are both in the second quantum number. So these are our orbitals. So we have 1, 2, 3, 4 electrons. So for carbon, we can say that we have 4 valence electrons. Okay, so that's just a very quick review of how we do electronic configuration. What does the atomic number, atomic mass mean? What are valence electrons? What's a very crude structure of the atom like? What's the structure of an atom like? Things like that. But what we're going to do here is, based on this, now we're going to go beyond, and we're going to talk about the first concept here, which is called an octet rule. Let me get rid of this. So we're going to discuss what's called an octet rule. Okay, and so what is an octet rule? Or in fact, before we discuss an octet rule, let's talk about compounds. Why do atoms combine to form compounds? Okay, so why do atoms combine with each other to form compounds? And the answer to this is to be stable, okay, or for achieving stability. Okay. Now, what do we mean by this? So for atoms, they have the way I would think about this is, when you have an atom, it is actually forming compounds to achieve the noble gas configuration. Okay, that is what an atom wants to do, to achieve the noble gas configuration. And what's special about the noble gas configuration? It is a complete or filled shell of electrons. It's a complete or a filled shell of electrons, and that is stable. So that's why, going back to Gen Chem, you might recollect that noble gases like helium, neon, argon, these elements, they are monoatomic. That means they do not form, or their preference is not to form compounds with other elements. Okay, they usually exist as monoatomic molecules. So what does that mean now? So for example, carbon, if you think about carbon now, we already said that carbon has an electronic configuration of 1s2, 2s2, and 2p2. Now the p orbital here, we looked at the electronic configuration earlier. There were 2 electrons here, 2 electrons in the 2s, and 2 electrons in the 2p. Now, this is not filled, and realize that the next orbital that's available is a 3s. So that's the next principal quantum number. So we do not have to consider 3s now. So for the second level to be filled, this orbital needs an additional 4 electrons, because again, recollect that P can go up to 6 electrons. So we can put 1 electron here, another electron here, and then we have 2 more electrons over there. So just looking at it in a very crude manner, this carbon should be able to accommodate 4 more electrons for it to be stable. Okay. And by doing that, 1s2, 2s2, 2p6, this would be the electronic configuration of neon. Okay, so an atom, okay, an atom like carbon, it forms compounds, or it enters into chemical bonding where it bonds with other elements to achieve the noble gas configuration, which is a complete shell of electrons or a filled shell of electrons, and these have been found to be stable. So the bottom line here is to become stable. How do they become stable? By getting more electrons. Now, what are the processes for doing that? We'll talk about it. So now if you look for something like carbon, when it becomes stable, okay, or when it completes its noble gas configuration, its valence shell, so it can take 2p2 and plus it can add 4 more electrons. So the valence shell now would have a total of 8 electrons. You have 2 electrons in the s orbital, and you could have up to 6 electrons in the p orbital. So this rule, because that number turns out to be 8, it is called the octet rule for second row elements. Okay, so this is for the second row elements. It's called the octet rule because it is because they're trying to attain that electronic configuration of the noble gas, which equals to 8 electrons in the valence shell. So it's called the octet rule. But now for elements in other rows of the periodic table, so for an element in the third row of the periodic table or the fourth row of the periodic table, they are also trying to attain that noble gas configuration, but it does not have to be 8 electrons in the valence shell. Okay, so the bottom line here is getting a complete or filled shell of electrons, but for elements in the second row of the periodic table. Now let me also mention which elements we're talking about, and these are the elements that we'll be discussing usually in organic chemistry. We're talking about carbon, nitrogen, oxygen, and fluorine. Now fluorine is a halogen, and this just represents any halogen. Okay, so for all of these elements, the octet rule applies because when they form compounds, they're trying to get to that magic number of 8 electrons in the valence shell, which is a complete shell of electrons. Now, how would this octet rule be achieved? We're going to discuss that in a subsequent video.